All right, so at the home stretch here. So the penultimate problem set is due today. There was a little bit of confusion. I meant to say that the stuff that's related to angular momentum in problem one is extra credit. That's a super tricky problem. But if you've done it, you get extra credit. There'll be one more assignment. That assignment will cover the material that we're discussing this week, which won't be on the final exam. So that problem set is an extra credit. Yeah.
So when does it due? Because Thursday, May 2nd is not a Thursday.
Oh, well, it's Thursday. What day is that?
Friday.
Well, anyway, it's actually, no, that's totally bad. It's totally wrong. So I meant the 9th, and that's a Friday. I meant the 8th. A week from Thursday. Yeah.
That's what I was thinking. That's why it's extra credit.
Yeah. Yeah. Right. So that's the last Thursday of class. Okay.
Excuse me, sir.
Yes.
For the final, is it going to be from lecture 1 to final lecture?
It'll be from lecture 1 until lecture 19B. Okay. I'll give you more. I'll re-emphasize all of these facts. But basically, the final exam will cover everything from the first day of class through the material that was last week, through radiation. It's not going to cover the material that we'll be discussing in these last 2 weeks. And our topic for this week is scattering.
You're introduced to
Dr. Gold just finished scattering.
Oh, well, there you go.
Yeah.
We're so in sync. Super. All right. So, and we'll see this in a number of years, this now like number for ways. So, you know, scattering is an important physical phenomenon. It's basically the way we learn about the physical world in general. We throw junk at it and we see how it scatters off of it, and from that we learn something about the nature of the interactions between things. Okay, and so typically the way that we characterize scattering is we have some kind of stuff. Stuff could be mass, it could be electromagnetic energy, it could be ping pong balls, whatever it is. There's some stuff that's flying along. Say, in this case, it's in some collimated thing. I can think about this as a bunch of ping pong balls, and here's my, so this is, these are my scatterers, right? The things that get scattered. This is my scattering center. It might be a bowling ball. And when these things, they scatter off of it. In this case, this is just R-sphere scattering, right? And you know, some of these guys will scatter in different, they'll scatter into different directions. Just depending on, in this case, this is just geometric scattering. And we see that there's a kind of effective cross-section that is presented to this set of objects. In this case, it's purely geometrical. And yeah.
Like, what would be the alternative to purely geometrical?
Well, when we think about things like waves, it's not a hard sphere kind of picture. What the effective cross-section here, it's literally the cross-section of the bowling ball. It's a purely geometrical thing because it's a mechanical effect. We'll see. Obviously, I'm setting this up as a straw man, so that we'll see in a moment of something that's not that. Okay? So, let me continue my rhetoric. All right? So we have this the whole notion of cross-section is motivated by this geometrical picture. There's a more generalized idea of cross-section we'll discuss today. Maybe you've discussed it. Quantum mechanics, when you think about the scattering from the point of view of Schrödinger waves. Okay? So, we can think about the rate stuff is scattered as equal to of stuff flowing per unit area times the cross section, which we typically call sigma. So the total rate at which ping pong balls are flying away, if I add up over all possible ping pong balls, I would get by the rate at which these are coming in per unit area, and then there's a cross-sectional area that captures that amount, and that cross-sectional area is this, in this case, okay? And so, generally speaking, what we call the scattering cross-section sigma is the rate of scattering, the total rate of scattering divided by the incident flux density. The flux density, I mean the rate at which the incident stuff is coming in per unit area. Okay? So that if I integrate it over an area, I get the flux, which is the rate. It's the rate at which stuff is coming in, and this is the rate at which stuff is going out, and the ratio between them, and this has the units of area. Okay? Right. So when we think about the scattering of electromagnetic waves, what stuff we're talking about electromagnetic energy. Okay? So if we think about the scattering of waves, then we would define the scattering cross-section in terms of the rate at which energy is being scattered, which is the power scattered, divided by the incident flux of energy, which is the rate at which energy is coming into the scattering center per unit area, which we call the intensity, right? So that's what this sigma is the effective cross-section presented to as if it were a bowling ball, but it's not necessarily the cross-section of anything, it's the effective area that is presented to the field that, in some sense, scatters the field, okay? And our goal is to find this for different kinds of problems. Now, often it is the case, as I kind of barely drew with any skill at all, that the scattering goes off in different directions, and the amount that goes into different directions will depend on the nature of the scattering process. So often what we would do when we think about, we have some, say, plane wave-like thing coming in, and we have some scattering center, and then we have, waves going out. And I might say, I want to know, I might put a pinhole, here, and I want to know how much is scattered into a given solid angle. Okay, so what I would be interested in is the differential scattering cross-section per unit solid angle, right? So if I were to ask how much is not scattered into all 4 pi steradians, but just scattered into this little pinhole which subtends some solid angle on the sphere, I would say, okay, there's some d sigma, that's the differential scattering cross-section, times the differential power scattered into that direction divided by the incident intensity, okay? And I can then say, okay, well, this is the differential scattering cross-section per unit solid angle, okay? So this is what we call the differential scattering cross-section per unit solid angle. And if we integrated this over all 4 pi steradians, we get the total scattering cross-section for scattering into all directions. So this is clearly a function of various things. The differential scattering cross-section is, when I think about this, there's some incident wave that I'm thinking about coming in as a plane wave-like thing. I mean, nothing's ever exactly a plane wave, but say we have some Gaussian beam where we're just looking near the center of the beam and it looks pretty planar. So there'd be some incident wave vector, and we're asking about the scattered waves into some direction. Yeah.
I just heard people sort of inconsistent about naming things. Will you be referring to just d sigma as the differential cross section, or d sigma d solid angle as the differential cross section?
I'll be inconsistent.
You'll be inconsistent as well.
Yeah.
Okay. Cool.
I'll be
Thank you.
inconsistent. I'll be inconsistent.
Okay.
It's both.
It's both.
Yeah.
Okay. Yeah. Cool.
Okay. So my differential scattering cross section per unit solid angle is a function of the incident wave vector and the scattering wave vector, okay? Now, I left a little space here because, of course, the waves are vectors, so it also depends generally on the polarization of the field, okay? So this will generally depend on the incident polarization and the incident wave vector and the polarization of the scattered field and the wave vector of the scattered wave. Okay, so it'll be a function of all of those things, generally speaking. When we have elastic scattering, and this term elastic scattering is motivated from this picture of the ping pong ball. If the ping pong ball has a certain energy and the bowling ball is so heavy it doesn't recoil at all, it's just a stationary object, then the energy of the scattered ping pong is exactly the same as the energy incoming ping pong. It just changes its direction. So elastic scattering is to say the energy of the doesn't change, okay? If for electromagnetic waves, that means that the frequency of the scattered wave is the same as the frequency of the incident wave, okay? That would mean the photon has the same energy because they're multiplied by h bar, then h bar omega of the incident photon is equal to h bar omega of the scattered photon. Yeah.
So for that, we're just borrowing that result from quantum and then keep going.
Well, that's not quantum. This comes from wave. This is wave theory. Quantum borrows it from classical wave theory.
So classically, we get that photons of different omegas.
Well, no, I'm saying the energies in this case. Yeah. Okay, so we call this elastic scattering, and we'll just, we'll call that omega. Okay. All right. So. Good. So now we can ask ourselves, what are these quantities given what we know from electromagnetic wave theory and what we've studied about our electromagnetic radiation theory. So firstly, what is the incident intensity given a plane wave?
Time average of the point vector.
That's right. So this is the time average of the Poynting vector. And in particular, we're looking at this along the direction of that. That's what our incident intensity is. And what is that? How is a Poynting vector defined?
C over 4 pi E cross B.
E cross B. And this is in free space, then this is the same thing as C over, the time average gives me an 8 pi times the magnitude of the incident field in the direction of the polarization. Okay, so the intensity is the square of the amplitude. That's why I forgot that stupid C over 4 pi and the damn typo, because we don't really care. It's just the square of the amplitude that I really care about, okay? Now, the power, we think about the power, the differential power radiated or scattered, I should say, we'll come back to radiated in a moment, into this solid angle is equal to the flux of energy through this little area, okay? So that's equal to the scattered Poynting vector dotted into the normal, which is k hat for the scattered, and then the area is what? Well, it's r squared d omega, where r is this distance. The distance from the scatterer to the detector, okay? So putting that all together, we get that the differential scattering cross-section per unit solid angle over here as a function of all that stuff, putting that in, is equal to, oh, and this of course is equal to, I'll just write it here, C over 8 pi, the amplitude of the scattered field in the direction of that polarization, the component there. So let's put that all together over here, and we get thus that the differential scattering cross-section per unit solid angle as a function of all that stuff is equal to the scattered amplitude squared times r squared divided by the incident amplitude squared. Okay. Yes?
So, just clarify, we have two different sigmas we're talking about here. We have one sigma that's the obstruction that things are bouncing off of. in the physical model, out in the wave model. And then we also have a sigma associated with the surface area or solid angle of the detector that's picking up the stuff bouncing off.
No, let me try to restate that again. The cross section we call sigma is the effective area that is presented to the stuff that scatters it. And it's defined in this way. It's defined in terms of the ratio of the scattered stuff divided by the incident flux density, okay? Now, to get the differential scatter in cross-section, let me get rid of this for a moment. We have this. This is just a differential form of this. But this is the power scattered into the physical aperture. And that, we said, is this. There's no sigma here. This is the actual area of this patch of the sphere. And that's how much power gets scattered into that little patch of the sphere. Does that make sense?
I think so.
And so, from that definition, when we plug that in, over here, I got d sigma is equal to the power scattered into that, which was equal to S scattered, that's the scattered intensity, this is the amount of power that's scattered into that little aperture, and this is the incident intensity. The ratio of these things is an area, which we call the differential scattering cross-section. If I divide by per unit solid angle, I get this, which we also call the differential scattering cross-section. Okay. So on the right-hand side here is what the field, the incident field is, what the scattered field is, and R squared. Yeah.
So something's a little bit confusing to me. At the very beginning, when you define the absolute cross-section, so I wanted to ask you that, is it possible to do that, or we have to get that from the differential cross-section?
Yeah, we have to get it from the differential cross-section and then integrate over all side angles.
So I was wondering why were we talking about the cross-section?
Well, what we could talk about, because it is also true, in order to this is a fact. The total cross-section is the total power scattered into all possible directions divided by its intensity. So that is, that equation is correct. But to calculate it, if we don't have isotropic scattering into all directions, we have to first calculate the differential and then integrate it. But this is not a false equation. And it's easier to start with the general idea and then, yeah. Yes, Omar?
If we think about it experimentally,
Yeah.
suppose we have something here and then
Yeah, a beam of stuff.
And this beam has an area,
Yeah.
but that's not cross-section.
No.
Because the cross-section is basically calculated by the effect.
That's right. And in fact, this picture, so I should have drawn it this way.
Yeah.
So the beam area is this, but the scattering cross-section is this in this geometric problem. So the area of the beam, the cross-section is the effective area presented to the beam that captures the scatterers and sends them into different directions. In this case, it's physically the cross-section of the bowling ball, which is why it's called the scattering cross-section.
And when we go to quantum mechanics, we just replace that idea with probability. We can think of all their like patterns.
Yeah, I mean, it's in the quantum theory, we would say there is, you know, the fraction stuff is the probability of the stuff being scattered. So let's focus on EM. Okay, you need to learn this too. Okay, so, good. All right, so what is the scattered wave? Well, that will depend on the nature of the interaction between the scatterer and the incident field. That will determine how the wave is scattered. Is it a chunk of metal? Is it a nitrogen atom? Is it a cesium atom? Is it a piece of glass? Whatever it is, there will be an interaction between the wave and the matter, and that will cause this thing to go into different directions. So the physics of that is there. So in particular, if we consider long wavelength scattering, so if this object has some effect, some size d, we're looking at the situation where the wavelength of the incident light is much, much bigger than the size of the scatterer. Okay? So this might be on the order of angstroms, and this might be on the order of, a half a micron. Okay? That would be an example of very long wavelength scattering. In which case, what we could say is that I have my incident field, I have my scatterer. What is going to happen is that I'm going to induce multipole moments. The incident magnetic and electric fields of this thing are going to introduce oscillating currents. And those oscillating currents will radiate. And as we've studied, and we're studying in the last weeks or so, the way it radiates depends on the Fourier components of that current distribution. And if it's long wavelength, that means that the lambda is much bigger, then we know that the dominant effect will be electric dipoles. Okay? So there'll be some, if I think about this, for example, as being linearly polarized in the plane, I'm going to get an induced electric dipole moment. Okay? And that induced electric dipole moment will radiate So scattering in this case is radiation. The field drives currents, and those currents radiate. So the re-radiated field is the scattered light. And if it's dipole radiation, then what is the scattered field given this at some distance r from the origin? What is the scattered field?
K squared, dipole perpendicular, and something else.
Awesome. And then it's a plane wave. I mean, it's a circle wave. Okay. So this is the induced dipole moment, and this is the field. Okay. Now, what is P? Well, that is a problem you can solve as an exact scattering problem. But let's for example, let's just start. Let's say that my scatterer, the thing that scatters, is a linearly polarizable particle. Okay, so we might say that my P, the induced dipole moment, let's make everything now a complex amplitude, is whatever the polarizability is times the field that induces it. Now, to the degree to which we neglect the back action of the radiated field back on the thing, to good approximation, we can take that field just due to the incident field. It's not exact. This is neglecting what I'll call the back action, which we'll study in homework next week. I highly encourage it. Yeah.
So it's like what we were talking about before, where we're ignoring the field effects of one dipole on its neighbors.
No, it's the field of itself. This is one dipole, so it's self-field. It's the problem of radiation reaction. It's the problem we saw in statics, where we saw the infinities that had to do with the fact that if we looked at the energy of a point charge, it was infinity because it's sort of the field on itself. But it is an effect that we have to really think about. As we'll see in the homework, it's a slippery slope because actually classical E&M doesn't solve it exactly. You really need to have quantum field theory to do it, but there's some essence of it that we can solve, and you will solve if you so choose to do it, and I encourage you in next week's homework. Yes?
In your vocabulary, I'm sorry, is the scatterer the incident plane wave, or?
No, the scatterer is the thing that scatters.
Okay, okay, thank you.
And so we're saying that previously we were looking at, say, like ping pong balls,
Yeah.
literally bouncing off stuff.
Yeah.
You were saying the waves aren't bouncing off of it, they get absorbed and move dipoles around, and then the dipoles radiate.
That's right.
Okay.
That's right. Now, we can try to think about a particle model of that, of photons coming in and hitting something. That's not what's going on. Well, what is hitting something anyway? It's up, right? I mean, when the ping pong ball is because its electron cloud overlaps with the electron cloud in the bowling ball, which causes, so. Okay, very good. So now what we have from that expression over here, putting this all together, this is k to the 4th alpha tilde squared times okay? Oh, no, not quite. I have to square this. There's a 1 over r squared. Let's cancel. That makes sense now. All right, very good. So now we have to think about this problem and the nature of the scattering, which will depend on the direction of the scattered wave relative to the incident wave, and also the polarization of the fields, okay? So if we can think about what we call the plane of incidence. The plane of incidence is the plane that includes the vector that is the incident wave vector and the scattering vector. So whatever plane that defines, we'll call that the plane of incidence, okay? And the direction of scattering relative to the incidence is called theta, okay? In scattering theory, this is the way we define it, okay? It's not the direction of the dipole that's induced, which could, in this particular case, is a dipole, but we're talking about the direction at which the thing is scattered. Now, as far as the polarization goes, there are two possible orthogonal polarizations, and we typically define them in terms of the polarization that's in the plane of incidence, that's parallel, that's called p polarization. That's in the plane of incidence. Linear polarization in the plane of incidence is called p polarization, sometimes called pi polarization. And the orthogonal direction, which is perpendicular, which is called S polarization. Why in the world is it called S? Well, it's called sigma because sigma is S, but why, if it's perpendicular, why would you call it S?
I like to think of it as it's standing on the.
Because it's, how do you say perpendicular in German? Streck or something, and it's, the Germans wrote this, so S is means perpendicular. That's where sigma polarization comes. It's the word for perpendicular in German, starts with an S. Okay, so S is perpendicular to the plane of incidence. And similarly here, for the scattered wave, this is the P polarization or pi polarization, and then the S polarization is perpendicular to the plane of incidence. Yeah.
On the last bit you wrote for the differential section where you have E scattered dotted or E scattered conjugate dotted into P perpendicular. Are the P there and the E on the bottom both complex, or are those the real?
Yeah, everything's complex. Everything's complex. I'm just not always putting this little doodad on it. Doodad. All right. Very good. So, and we have in this case, we're going to have a P induced. That's going to be induced by P polarization. Excuse me, too many P's, too many sigmas. You know, it's life. I'm sorry. And we have P induced for S coming out of the board. Okay. The perpendicular component of that is going to be along one of these polarizations, right? Okay, so let's look at the differential scattering cross-section for, say, P polarization as a function of theta. Okay, so I want to know, given P polarization, how much is scattered into P polarization as a function of theta. Okay, so that's given by what? Well, we have the general expression, that's k to the fourth, the magnitude of the polarizability squared, and then we need the magnitude of P perp for P polarization squared, divided by the I forgot one thing over here, right? When I wrote the P, oh yeah. So there's too many things. This is not, I didn't do this correctly. Okay. Sorry, I substituted this in, but I didn't substitute it in correctly. So let's go back to this. I'm trying to do it without my notes. So this is k to the fourth, right? K to the fourth, the magnitude of that, and then the magnitude of this. Okay, so let's. I think that's correct now. Okay? So what is P perp in this case as a function of theta?
It's E and E scat.
So this is, if this is P, then which angle is theta? Theta is this. Right?
Yes. Magnitude of P, magnitude of E, sine of.
So this is equal to the magnitude of P induced squared cosine of theta squared. Okay? Divided by E incident. in P polarization squared. But the magnitude of P squared is equal to the magnitude of the polarizability times the incident field squared in the P polarization, which is the magnitude of alpha squared times the magnitude of the incident field squared. And so putting that all together, I get k to the fourth, the magnitude of the polarizability squared, and I think that's it, times cosine squared theta. Let me check my notes. That's right. So this is the differential scattering cross section per unit solid angle, given P polarization of the incident field and detecting P polarization in the scattered field as a function of theta. Yes?
Would this be any different for S polarization?
It will be. We'll do that in a moment. So before I do that, I ask you, does this have the right units? Oh God. Well, firstly, what is the units on the left-hand side?
Area.
Area. Right, so there's units of length squared on the right-hand side. What are the units of K?
1 over length.
1 over length. So we have length squared is equal to 1 over length to the fourth. And what is the units of the polarizability? Oh God.
I hope it's length squared.
Well, it need to be like Q,
Oh.
but
No.
unionless, right?
No, maybe.
So let's remind ourselves, we have the dipole moment, right? Which has the units of charge times distance. The electric field has units of charge over distance squared, so this has the units of distance cubed. Okay, good. It's good to check the units. That's how you know you did at least something right. Okay? Very good. If you had epsilon and that, you'd be screwed. All right. So let's answer Benny's question. What about when I have S polarization? So when I have S polarization, let's just draw the picture for a moment before I so now the field is coming in and it's oscillating like this. And we have an induced dipole, which is oscillating like that. How does it radiate as a function of theta in the plane of incidence? How does the amount of, what is the perpendicular component of P perpendicular to the direction of propagation? It's the same, it's isotropic. So no matter what I am, I'm going to see the same amount of radiation as a function of theta. So for S polarization, we get the same expression that's independent of theta. Okay? So what that means then is the following. If I send in light, let's say the light is what we call unpolarized light. It's not a superposition of S and P, but a so-called statistical mixture. So that means some of the radiators radiate like this, and some of the radiators radiate like that, and I don't know which is which. And so this we would say, if I have a 50-50 mixture, of S and P we would say this is unpolarized. Okay. Now suppose I send this on this dipole, induced dipole, what am I going to see? I'm going to see a statistical mixture of these two radiation patterns, right? So if I look at theta equals 0, then I have a perpendicular component of P and a perpendicular component of S, which are equal, and I'll have a 50-50 mixture of S and P polarity. It will be completely unpolarized for forward scattering. But if I look at 90 degrees, then I can't radiate P polarization. I only radiate S polarization. So this is polarized, 100% polarized, and it'll be purely S, because none of the P polarization can scatter into that direction because it can't radiate into that direction. If I look at some other arbitrary angle, I'll have what I'll call partial polarization. There'll be more S than P, but there'll be some amount of P polarization because there's some amount of component of P polarization that's perpendicular. Yeah.
Is it just a coincidence that these look like the S and P orbitals, or?
That's just a coincidence.
That's just a coincidence?
Yes, that's just a coincidence. Yeah, just a coincidence. Just a coincidence.
Okay, cool.
Interesting, but yeah, not related. Okay, so we could look at what we call the degree of polarization. I'll call it capital Pi because that's what Jackson calls it, as a function of theta, which we'll look at as the difference between the scattering cross-section, differential scattering cross-section per unit solid angle for S and P, divided by their sum. Okay? So if they were equal, then I would stay completely mixed, but if this guy is 0, then I have completely polarized. So this pi doohickey, again, according to this, is going to be 1 minus cos squared theta over 1 plus cos squared theta, or sine squared theta over 1 plus cos squared theta. Okay. We can talk about the total. So what's underneath here is the total differential scattering cross section. It's the sum of how much is scattered into S and scattered into P. Okay, yeah.
So we sweep from 1 to -1?
It's squared. So it
Okay.
goes from, so if I look at this as a function of from theta goes from, say, 0 to 90 degrees, or 180 degrees, this thing kind of looks like this. So when I look at 90 degrees, I have, this is fully polarized, and in the forward and backward direction, it's completely unpolarized, okay? assuming my incident field is completely unpolarized. And if I were to calculate the total differential scattering cross-section as a function of the angle, what I see is that I get the most scattering into the forward and backward direction, but only half of it scatters to 90 degrees. So if I were to plot that on the same kind of scale with a different set of axes, I'd see something that, looks like this expression, 1 plus cosine squared theta. So this I'm plotting here is the total scattering cross-section divided by the maximum value. Okay, so I get the most scattering into the forward and backward direction and half the scattering at 90 degrees. Because I cannot scatter the polarization that is oscillating like this because it does not radiate into that direction. Okay? Very good. Yes?
So this is essentially telling me about the geometry of the radiation, right? So why do we define it in terms of differential cross-section? Because that's a property of the scatterer.
The differential scattering cross-section we need to calculate, as was discussed earlier. If I want to get the total, which we'll get into a moment, generally the amount of scattering I get into different directions depends on theta. And that's a differential thing. The amount of scattering that happens into a differential area on the sphere divided per solid angle is this. Okay? So I'm not sure I understand the question.
All I'm asking is, I can basically see that, okay, when it is 90 degrees, there's not as much
That's right.
polarization.
Right.
So when we define it like that, so there's alpha there initially, that cancels out.
Yeah, well, the alpha was just, these expressions are just another fact about the nature of the scattered light, that the way in which scattering happens in different directions depends on polarization. And that fact we're quantifying in terms of this ratio. But that's not the only thing I might be interested in. I might want to know how much energy I'm going to scatter into a particular direction per unit side angle, and then I need to know this thing. And in fact, let's do that. So let's calculate the total scattering into all possible 4 pi steradians and to all possible polarizations. So the total scattering cross-section sigma is the integral over all solid angles of the scattering into both S and P. Which is equal to k to the 4th alpha tilde squared integral over all solid angles of 1 plus cosine squared theta. Because that's what we got for the total. Okay? So that's something we can integrate. Remember here that theta is defined relative to the polar axis defined by the incident wave, and the azimuthal angle phi swings around this in a a nuclearly symmetric way, right? And so what is d omega? Well, it's d phi sine theta d theta, but this is independent of phi, so I'll just call that 2 pi. And then it is always best when dealing with cosine theta to write sine theta d theta as d cosine theta. It's the right change of variables to me. I'll call this thing mu. Mu goes from -1 to 1 because theta goes from 0 to pi. And so when you do these integrals, that's what you always do. You change variables to mu equals cosine theta, and you do your change your variables. And this thus is equal to 2 pi k to the 4th, the integral from -1 d1 d mu times 1 plus mu squared. Okay. And we can do that integral as mu plus mu cubed over 3 from -1 to 1, which is equal to, oh, gee, there's one thing I forgot. Let's go back over here. I forgot about this thing. The fact that we have a 50-50 mixture, which means only half of the intensity is in one and half of the intensity is in the other. So the total scattering cross-section for each of these guys, if I had 50-50 mixture, would be a half of this and a half of that, right, for 50-50. So my actual scattering cross-section in this case will be half of that. It's a half of one and half of the other. All right, so I got a half over here, and when I put that all together, I get 8 pi over 3 times k to the 4th alpha squared. That's the total scattering cross-section. Okay. All right, so now we have to think about the physics of what the hell the polarizability is. Well, that will depend on the stuff that is being polarized, okay? We can think about the example of the Lorentz oscillator model. Where we think about this as a charge on a spring with some restoring force and resonance frequency omega naught and some damping, right? And we calculated in this case what the polarizability was when we were drive this with an incident field. And what we found lost any factors there. That's right. Yeah.
You said that our sine d theta is the same as d cosine theta?
Minus.
Okay.
But then you have to change the limits of integration,
Okay.
and it all works out.
Okay.
Yeah. Okay. So this is our general expression if we thought about the matter as a bound electron that's bound to the nucleus, and it gets a harmonic restoring force when it's being driven by the electric field, okay? We have to think back and remember that. Now, we can think about this in different limits. We can think about what if I'm scattering right on resonance, what if I'm scattering off resonance. But of particular interest is the case where omega is much, much bigger than omega naught, but still lambda is much, much bigger than p. Okay? Then, in that case, the polarizability is this guy is much bigger than this, and that's much, much bigger than that. So this is approximately E squared over m omega squared. This is really equivalent to thinking about a free electron, like in a plasma. In this limit, that's the effect of what the polarizability is approximately equal to. And so what's the total scattering cross-section in this case?
Omegas cancel.
And the omegas cancel in this case. And this becomes that. Okay? Now, does this have the units of cross-section? This has to be an area, which means this must be a length. In fact, that length is called the classical electron radius. Let's talk about that. So the classical electron radius is defined to be E squared over the mass of the electron times the speed of light squared. It's a definition. Why would we call that the classical electron radius? Well, I can also say that says that the rest energy of the electron, mc squared, is equal to E squared over this radius. And what is E squared over that radius? E squared over that radius is the electrostatic potential it would take to take a charge of E and squeeze it into a sphere of radius r. So, you know, when this came up, I guess Lorentz saw this and said, hey, maybe that's what the radius of the electron is. We actually don't think that's true. In anything we've measured, we've never seen the electron have any radius at all. It's a point. But it is a constant that appears when you have the electron charge, the mass, and the speed of light. You get this radius. And it comes into the scattering cross-section, which is known as the Thomson scattering cross-section. So this scattering of a free electron by an electromagnetic wave has that scattering cross-section, which looks like the electron has that cross-sectional area proportional to the square of its classical radius. Okay. Yes?
So the ball has charge E, where is the E squared coming from? We're saying it's interacting.
Well, then you have to remind ourselves of what is the potential energy associated with how much work I would have to have done to squeeze that charge from infinity into that ball. That's how much work I would have to do. All right, let me continue and let's look at an important question. What is in the situation where I look at the opposite limit when omega is much, much less than omega naught, but at the same time, omega naught is much, much bigger than gamma. In that case, the polarizability is approximately E squared over m omega naught squared. And when we then get what the total scattered cross section, this is known as the Rayleigh cross section, because Lord Rayleigh did this first. And the answer we get when we plug that in with omega naught is equal to the Thomson guy times the ratio of omega naught to the fourth power. Now, what we notice here, in Thomson scattering, as long as my frequency was big compared to the binding energy, it was independent of the frequency. Like here, in this regime, we have quite the opposite. This is a very strong function of omega. And we understand where that comes from because the scattered radiation is a strong function of omega because the amount of power that's radiated is proportional to the square of the acceleration. And the acceleration is proportional to omega squared. And so the square of the acceleration goes like omega to the fourth. So that's a very strong function of omega. It means high frequencies, as long as I'm well below resonance, will scatter much more than low frequencies. And this was how Lord Rayleigh explained why the sky is blue. Have you ever seen that argument?
See the demo.
Seen the demo. And now you know the math. Well, we can look at this a little bit more carefully. So, here's the atmosphere, got some thickness to it. So, why the sky is blue is the dominant scatterer the thing that does the scattering in the atmosphere is nitrogen molecules. Okay? And the nitrogen molecules have their resonance omega naught gives a frequency of about 450, no, what is it? I don't remember. 26 is UV. All right. Yeah, 75 nanometers. So visible light, you know, some few hundred nanometers, has a much longer wavelength than this. Yeah.
And the resonant wavelength being the point at which it is
would-
most susceptible to induced dipoles.
That's
and
right.
radiates from.
It's where we would be, that's where the resonant binding is, okay? So here's the sun. Okay, and here am I. A little bit of hair. I'm happy with the sun. And the sun is white light. And we know that we have forward scattering and the sun looks white. Okay, all the light that comes out forward. But if we look off from the sun, then we're seeing light that's scattered in some direction. And not all colors get scattered equally. The higher frequencies get scattered much more than the lower frequencies, which is why the sky is blue. But hey, actually, why isn't the sky purple? Because the purple will get scattered more. So if we look away, the light that we're seeing, we should see the purple color more than the blue color. Why isn't the sky purple? Because there's definitely much more purple light scattered than blue. Yeah.
Does the atmosphere absorb that before it gets?
No, it doesn't actually. It's a good thought, but it's not actually what happens.
Oh, we got quite the right angle.
No,
Does sun itself absorb the photon?
no. All that light is coming to our eyes.
I can't detect it.
That's right. Our eyes are not equally sensitive to all colors. So there's a filter. Our eyes are more tuned towards the green than the violet. So our eyes filter out more of the purple light than the blue light. That's why otherwise what's actually hitting us, if we were sensitive to the sky, would be purple. Wouldn't that be nice? I'm sure there's some animals that the sky would see the sky as purple, because there's more purple light coming to us, okay? Yeah?
And why is it when you take a picture, like like if you have like an LCD camera,
Yeah.
that's getting all the purple light?
Well, that's a good question. I don't know the answer to that. We'll have to talk. And it might be that the cameras are set, I mean, they're digital so that they, you know,
They have filters
to
that take
reproduce
off.
what the eyes look at, but I don't know the answer to that.
Maybe the picture has also the purple, but your eyes still have the filter.
I know they put filters to take out like IR and stuff. So they
Was
probably
it-
have filters to take
Yeah,
out.
it's a good question. I don't know the answer. I don't know the answer. We'll have to research that. Google it and let me know on Thursday. Okay, on the other hand, from my lovely home, I can see when I'm sitting there writing your homeworks again and the sun is not at the zenith, and a lot of the light gets scattered out, and the light that comes to me, I'm in horrible daylight savings time when I'm mad because it's 10 o'clock and it's still sunny. And the light that comes through here is redder, because the blue and violet lights are scattered away, and what transmits more, so there is attenuation of light by scattering. And in fact, the higher wavelengths are more attenuated. Now, why it's not true here is that the difference is the effective thickness of the atmosphere is much less at zenith than when I'm on the horizon, because it has, depending on the angle. So we'll calculate that next time to see what fraction of the light is attenuated when I'm at zenith versus when I'm at sunset. there's a thicker amount of the atmosphere that I have to propagate through, and so that attenuation becomes noticeable to us at sunset, but not at noon. Hooray! Why isn't the picture purple? We'll have to find that out. All right, I'll end on time today. Have a good afternoon, everybody.
Deutsch?
Yes.
You mentioned this is because of the accelerations dependence